Good morning, everyone. Today we're going to be looking at lesson 97 together. We're going to be talking about similar triangles and indirect measure. So we have to understand in this lesson what similar triangles are before we can understand how to use indirect measure. So let's go ahead and start into the lesson. If you want to turn in your textbooks to lesson 97, it begins on page 664, and you will see the title of the lesson there. So let's go ahead and look at an example that I'm going to draw down on the bottom here. Similar triangles. Let me just draw a couple for you so you can kind of see what they are. Now keep in mind, we've talked about similar triangles in the past. Similar triangles have the same shape, but not necessarily the same size. Makes them similar. But how can we know what's the criteria for them to be similar? Well, let's consider triangle ABC and triangle XYZ here. Okay, now I'm just freehanding these, but you can imagine that if this was real measurements, they would look a lot neater. But I think for this example, they look just fine. So I'm going to mark up a couple of angles. One of the things that you have to know about similar triangles is that all of their corresponding angles are congruent. So I mark those by these little tick marks. So when you see in a triangle a tick mark between two different, or it could be in the same triangle, but for the sake of similar triangles, you're going to notice that you have congruent angles here because there's a tick mark here and a tick mark here. Now, angle B and angle Z are also congruent. They are similar triangles, and if they're similar triangles, their angle measurements or corresponding angle measurements are congruent. Now think about this. The sum of the angles of a triangle are 180 degrees. So if angle A and angle Y are the same measure, and angle B and angle Z are the same measure, then it stands to reason that angle C and angle X would also be the same measure, or congruent as we would call it. Okay, so that is the criteria to having similar triangles. Their corresponding angles must be congruent. And once you've established that, and you know now that we have two similar triangles, now we know that all corresponding sides are proportional. They're obviously not the same length, right? Because this triangle is larger than triangle XYZ. So their sides are not the same length, but what we're going to discover today is that they are actually proportional. So let me show you an example here. I'm going to draw, first of all, let's go back up to the top of our notes because we have something to fill in here. Similar triangles. Let's fill in here that the length of the corresponding sides are proportional. Okay, now I'm going to draw another set of right triangles here, and I'm going to show you an example what I mean by having proportional sides. So here is a triangle with sides 6, 10, and 8. It's a right triangle, and we're going to mark up a couple of the angles here. And then I have a smaller triangle that has the same right triangle, and its sides are 3, 4, and 5. And we're also told that we have some congruent angles. Okay, so now we know we can establish in our minds that these are similar triangles based on the knowledge that we have with regarding their corresponding angles. All corresponding angles are congruent, and so therefore their sides should be proportionate. We're going to call this one triangle A, and this is going to be called triangle B. So watch what happens. I'm going to show you two different strategies here. If I have, I want to put A on the top. If I have triangle A and I set up a ratio over triangle B, and I'm going to set up some proportions here. So I'm going to look for corresponding sides. We just wrote something up top about corresponding sides, and their sides should be proportionate or proportional. So I'm going to find corresponding sides. Well, how do I know which sides are corresponding? Well, you look at the position of your triangles and you figure this side with this measurement of 6 corresponds with this one, the measurement of 3. So in triangle A, we would have 6 over 3. Let's find another one. Let's find Let's do the long one next. So I have 8 and 4. And then finally, we have this one, which is called the hypotenuse. And we have 10 over 5. Now, the interesting thing about each one of these, think about this. 6 divided by 3 is 2. 8 divided by 4 is 2. And 10 divided by 5 is 2. What does that mean to us? What that tells us is that the larger triangle, triangle A, is 2 times the size of triangle B. Now, my drawing doesn't really show that to scale, but with the side measurements, if we actually did this with a ruler and used maybe millimeters or something like that, it would be twice the size. And you can tell that by actually even just looking at the sides. 6 is twice the amount of 3, 10 is twice the amount of 5, and 8 is twice the amount of 4. So it's like they took triangle B and just exploded it 2 times to become the larger triangle. Now let's look at it. What about if I write my proportion the other way around, where I put triangle B on top and triangle A on the bottom? Well, let's write those down. So now I have 3 over 6, because I'm writing the measurements from B on the top and A on the bottom, and 5 over 10. And each one of those is going to turn out to be 1/2. And all that tells us is that the smaller triangle, B, is half the size of A. And that's easy to see. Just like I said, you could have looked at these triangles up here and noticed the relationship between those measures of those sides to see just how much smaller or larger each one of those triangles are. Similar triangles. Okay, so we can write proportions using equal ratios to find lengths of unknown sides of similar triangles. And we're going to do this example. This one goes into your notes. You're going to notice at the top up here, actually I can come all the way back up here, and we can see this up at the top. Okay, you have this pasted in your notes as well. 2 little triangles there. The sides are 5, 3, and 6, and the smaller triangle to the left. And on the right side, we have one side is 10, and A is on the other. We do not know that one, and we are to solve for A. We're supposed to estimate the length of A. So I'm going to kind of look at the relationship between the measures of the angles I have. I need to change this one so I can read it. On mine, it's very blurry, so I just need to fill in a 5 here, and 3, and 6, so I can see it a little bit better. And then we have A here, and 10. Okay, so let's look at our corresponding sides and see if we can see any relationship at all. Well, it's hard to look at 6 and 10 and see any relationship between those, but I'm going to kind of look within one of the triangles. So I'm just going to look over here and see, well, what are my sides actually doing here? Let's kind of look at this side and this side. The side on the right here, that's measurement of 3, is half the amount of this side. So I'm going to just use that strategy to say that I think, I'm going to estimate that this is going to be 5. But we're going to come back and actually test that. So the first thing we do is we should always evaluate whether or not the triangles are actually similar. So let's ask ourselves some questions. Are the corresponding angles congruent? Yes. We see here that we have tick marks here, here, and then we have 2 here, which tells us there are actually 3 corresponding angles, because if those 2 are congruent, well, then that means the remaining 2 are also congruent. So yes, corresponding angles are congruent. We took care of that. And are corresponding sides proportional? Yes, they're going to be. If all angles are congruent and we've established that we have 2 similar triangles, then we know that all corresponding sides will also be proportionate. So let's look at our triangles now. Number 2, one says to identify the corresponding sides. So let's look at side length that in the first smaller triangle that has a 6, and then figure out what is the corresponding side in the larger triangle. Well, 6 is right here, and the corresponding side to that one is here. The nice thing about these is these are positioned the same way, so it's easy to see which sides go with which sides. Side length 3 in the smaller one, which was right here, corresponds with A. Okay, so now number 3 tells us to set up a proportion and solve. So off to the right here, you have a little box where you're going to write this proportion. Blow this up a little bit. There we go. Okay, so we're going to set up the proportion just like we see it right over here. I have 6 and 10 and 3 in A. So those are going to be my corresponding sides. So I'm going to do 6 is to 10 as 3 is to A. There's my proportion. And we're going to solve from there using our cross product. 6A equals 30. We divide both sides by 6. And I'm left with A equals 5. Interestingly enough, you notice that is what we estimated right here. So our estimate was correct using another strategy. And then in the final end, to actually prove it, we used a proportion in our cross products, and we found that the measurement of that side is actually 5. Okay, now, how do I use this in a real life situation? I'm going to show you an example down at the bottom here. This is not going to go in your notes. The story was a little bit complicated when I was reading it out of the textbook. It was a lot of reading to get through this problem and understand what was going on. But as best as I could understand it, here we go. Here's what happened. So there's a tree somewhere, and there are 2 girls walking through the park, perhaps. One of them is Sarah, and one of them is Beth. And one of them says, gee, I wonder how tall that tree is. And her friend says, I don't know, but we could figure it out. And actually, I want to move this one over a little bit so we can make some room. And I want to add to this that it's a sunny day. So we have sun up here in the corner that's casting down and making shadows of our objects that are standing on level ground. So let's take our tree, and I am going to make the shadow of the tree here. And then Beth is standing over here, and she has a smaller shadow because she's obviously not as tall as the tree. But remember, their angle from the sun is going to be the same. So as it's casting down, we can use that information to figure out some measurements that we need to figure out, which is going to be the height of the tree. Okay, so Beth says, I'm 5 feet tall. Now what I want you to notice before I move too much further is here's what happens. I'm going to go from the top of the tree down to the tip of the shadow with a dotted line. Okay, and then I'm going to bring this down and make a perpendicular line to the level ground. And I'm going to bring this over. And look what I made. There's a triangle. Then, the same thing with Beth, we're going to do. And from the tip of her head down to the end of her shadow. And she's going to come down and make a perpendicular line. My shadow's a little bit shy of where I needed it to be. So we'll just bring it out here. And we'll just add it on a little bit. The shadow is actually out a little bit further. Okay, and now I have 2 right triangles here with my 2 objects. Now I'm going to move those out in just a moment, but just think about that, okay? That gave us the opportunity to see a right triangle, 2 similar triangles, 2 different objects, one bigger than the other, and we have 2 right angles, and because this dotted line on each one of those is coming down at the same angle, we know that the angles within here are going to be congruent. So therefore, I have 2 similar triangles. Now let's pull those out from there. Write them here. Okay, so here's some information I'm going to plug into my, to label my objects. This is going to represent, this side here represents the height of the tree, which, by the way, is what we're trying to solve for. That's what we want to know. What's the height of the tree? Beth knows that she is 5 feet tall. This is going to represent the height of Beth, and she is 5 feet tall. She knows that. She's estimating that her shadow, which I don't think I did a good job here of copying that down well, but it's okay. Just stick with me here. She estimated that her shadow length was 6 feet, and that is the shadow of Beth. And then we have the shadow of the tree, which she estimated as being 30 feet. Shadow. and this is height on each one of our triangles. Okay. Now, I'm going to use proportions to solve this. Actually, there's a couple things that I could see here. I'm going to notice that my shadow, and the question is, well, how did she estimate that? Well, maybe she took, some people can estimate what a yard looks like, or, yardstick, or a foot, 12 inches. And perhaps she just walked it to see how, or her friend was with her. So perhaps her friend just walked the length of her shadow and said, it's about 6 feet. And then walked the same exact way, walked the shadow of the tree's shadow, and determined that it was 30 feet. But those are estimated. But regardless, what I can notice is there's a relationship between 30 and 6. I notice that 6 is 5 times smaller, or I could say 30 is 5 times larger than 6. So there's probably a good chance that the height of our tree is going to be 5 times the height of Beth. So if that's the case, I could do 5 times 5. I'm just going to estimate this to get 25 feet. Okay, so let's use our box, our ratio box, to figure this out. So I'm going to draw one right down here for us. And I'm going to set it up and label it. You don't have to do this in your notes, guys. I just want you to follow along. This is going to represent the height of the object. The other column is going to be the length of the shadow. And this is going to be Beth's info, and this is going to be the tree's info. So what do we know? We said that the shadow of Beth was estimated to be 6 feet. Ooh, what was that? And the shadow of the tree is estimated at 30 feet. Beth says she knows that her height, the height of Beth, is equal to 5 feet. She's a little bit short, but then again, I'm only 5'1", so she's not too short, I guess. And then the tree's height is what we're trying to figure out. Okay, we believe it's going to be 25, but let's use the math that we've been learning to use our proportions to see if that is, in fact, the truth. We always have to prove things here. So let's take our information and set this up. So I have the height of Beth over the height of the tree equals the shadow of Beth over the shadow of the tree. There's the proportion. So what is the height of Beth? The height of Beth is 5 feet. The height of the tree, we don't know. That's what we want to figure out. The shadow of Beth is about 6 feet. Using the same method to determine the shadow of the tree, it was determined that the tree's shadow length is 30 feet. Now let's use our cross products. I have 6 HT equals 150 feet. We divide both sides by 6. We find out that the height of the tree is, in fact, 25 feet. So our estimate was not just close, but exact, provided that she estimated the correct measurement of the shadow and for her and for the tree. But the height of the tree is 25 feet. Okay, so that's 2 different ways to think about it using your ratio box, which is going to be probably the most common way of doing it. But if you were actually standing out in the park and you were the one trying to figure this out, you would probably have used this method right here, where you're just going to figure out the relationship between the sides to determine the height of the tree. Okay, now let's go to our notes, because we're going to do one of these in our notes. Example 2 says, to indirectly measure the height of a light pole on her street, Jenna measured the length of the shadow cast by the pole as 24 feet and the length of the shadow cast by a vertical meter stick as 40 centimeters. About how tall was the light pole? So let's do some labeling here first. Let's get our objects with some measurements on it. Our objects are turned into right triangles. So we're going to put our right angle measurement in here. We have the pole over here. We're going to call that height of pole. That's the height. The shadow is 24 feet, is what we were told in the problem. The shadow of the meter stick was 40 centimeters. and the height of the meter stick is 100 centimeters. Okay, so we're going to use our ratio box to solve this. So the first row is going to be information about our meter stick. The second one is going to be about our pole, the light pole. And so let's fill in what we know. We know that the height of the meter stick is 100 centimeters. The height of the pole is what we're trying to figure out, so we don't know that one. So we'll leave that as HP. The length of the shadow of the meter stick was 40 centimeters right here. And the length of the shadow of the light pole is 24 feet. Okay, so let's set up our proportions. Now I notice I have centimeters and feet here, so we're gonna probably need to be doing some conversions here. So let's write down every piece of knowledge that we have here. So we have 100 centimeters. So this is the height of both objects set up as a ratio, and we're gonna set that equal to the ratio for the length of the shadow, which is 40 centimeters over 24 feet. And now I have my proportion. We're going to do cross products here. So I'm going to have 40 centimeters HP when I do this way. And then we do the other way, equals 2,400. Whoops, excuse me, I don't want to put that there yet, sorry. Let's write down what that we're actually multiplying here. 24 feet times 100 centimeters. Now I want to isolate my variable of HP, so I'm going to have to divide both sides by 40 centimeters. That is going to cancel out some stuff over here, so we want to make sure we cross that out. So our 40s get crossed out and our centimeters get crossed out. So I'm left with HP. I'm going to do some cross canceling over on the right side of my equation because these are set up as products on top of your ratio, and so I can cross cancel between all of those. So first thing I notice is I can divide both of these by 10, so I have a 4 here and a 10 here. I can cross out my centimeters. I can continue on. I can get 1 4 here and 6 here. And then what's left is 6 times 10 and the feet. So what is left is 60 feet. And that is the answer to that. So the height of the pole, let's put that in over here, is 60 feet. So let's look now. It's kind of hard to see the relationship between the centimeters and the feet. So the conversion helped us, though, to get to the final answer there. But that's how you figure that out and you make your conversion. Okay, so, well, you make the conversion simply by doing your cross canceling. That's what ends up converting it back into feet because we can cancel out our centimeters. Okay, I did have one more that I was going to show you, but I think I've gone long enough, and I think that you've gotten 2 good examples here, the one in the park with the tree, and then the one with the light pole as well. So similar triangles, please remember what qualifies triangles as being similar is that they have corresponding angles that are congruent right up here, and also that means then that their sides will be proportional. And that's how we know that we have similar triangles, and it helps us to solve many problems in the real world as well. Okay, guys, you have a great day. I actually will be seeing you shortly on Zoom. Thanks for watching.